All right, so now let's talk about a different topic. So for the next set of slides, I will introduce hidden Markov model, and this is in the context of partial observability. Okay, so here the framework that we've been working with is the following, where for reinforcement learning we've got our agent, it executes some actions, then these impact the environment returns some reward as well as a state. But now some of you have been asking already in the previous lectures, now this state, right, like why can we assume that really the environment is going to reveal its state completely, right? So what is more common is that the environment does not reveal the state, but simply provides an observation. Okay, so here, what I mean by an observation is that it's going to be some information, right, but it might not be the complete information, or it might not be the exact information about the state of the environment. Okay, so we're going to see some examples in a moment, but this is a more general setting that would correspond to a partially observable environment, and then we need to be able to deal with this in many situations. Okay, so let's go back to Markov processes. So if you recall, when we started the course, the first topic that we discussed was this idea that whenever we've got some environment, perhaps we can model how its state evolves over time through a stochastic process. And then here we made two assumptions, right? The first assumption is that the process is Markovian, and here we really meant first order Markovian, right? And if you recall, that means that the probability of a state given all the previous states is equal to simply the probability of a state given the immediately previous state, right? So in this graph, right, so if I look at S3, it depends only on S2, and it's actually independent of S1 and S0 given S2, right? So this was the Markovian assumption. And then we made a second assumption where we said that the process is going to be stationary, which means that the distribution to obtain S3 given S2 would really be the same as the one to obtain S4 given S3. So in other words, it doesn't matter what time step we're at, right? The process will have the same dynamics, the same conditional distribution. Okay, so now let me introduce hidden Markov model, where the idea is that instead of just having a process with some states, because the states might not be directly observable, we're going to create another set of random variables that I'm going to call observations, and these are going to be correlated with the states. So as an example, if we consider robotics, right, so a robot might be our agent that does some reinforcement learning, and then it's in some environment. Perhaps it needs to go from one location to another, and then to know the state of the environment would mean that it knows its location, and it knows perhaps which direction it's heading, and so on. But the reality is that robots, mobile robots, it's not obvious for them to know their precise location. So even if you use an odometer, the robot eventually will get lost. And then so here it needs to use some sensors. So in robotics, information about the world are obtained through sensors. And then the sensors, they really just provide observations that are correlated with the state, but are not necessarily equal to the state, or they don't necessarily capture everything that's necessary to obtain a state. Okay? And you could argue that in pretty much everything, it's very rare that you get the full state. You typically get something partial about the state and also something noisy about it. And then, so that's why we're going to distinguish now the true underlying state from the information that we get. And information that we get, we're going to call that the observation. So one way of modeling this is through a hidden Markov model, where the idea is that instead of assuming that we observe the state at every step, we're going to say that we observe something else that we call the observation, and then these observations are simply going to be correlated with the states, and then perhaps we can model this through an observation distribution here that says that if I'm in a certain state, there's a distribution over the observations that I might receive. Okay? So, yeah, so basically a hidden Markov model, you can think of it as an extension of a Markov process where what we've done is now added another set of random variables that are observations that are correlated with the states, and now the states, we don't assume anymore that we can observe them, so they might be hidden. And this is where the name comes from, hidden Markov model. Okay, so a good example here would be, for instance, speech recognition. So in fact, hidden Markov models became very popular with the task of speech recognition, where here the observation is some signal. So here I've got some acoustic signal in the frequency domain. It actually corresponds to variation in the air pressure that's produced by sound. So sound is really just a variation of air pressure. And then the idea is that this, for us, when we hear somebody talk, right, what we think immediately is like, what's the meaning of what the person said? Like, we clearly hear what the person said, but I mean, from a robotics perspective, or otherwise from the perspective of a machine, right? So what a person said is really just variation of air pressure, right? And now there's a problem about how do we translate these variations of air pressure into actual words, right? So if somebody says Bayes' theorem, it might actually look like this when you plot this into the frequency domain, and this might be the amplitude as well. And then this could correspond to various phonemes. So Bayes could be decomposed into 3 phonemes, and then theorem could be decomposed into 4 phonemes. Okay? So now here we could say that the observations are the signal, and then the hidden states are essentially the words that a person said. Okay? So then hidden Markov models were used many decades ago with great success initially in the context of speech recognition, and this was the idea that we have some signal that correspond to the observations, and then we have some words or otherwise phonemes that correspond to the hidden states. Okay, so as another example, if we consider a mobile robot, here a mobile robot, so we might put the robot in a specific location, and then let's say we give it some commands that would say go right, 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 and then up, 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 and then left, 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 left. And here, what this graph shows is that at every point here, or every dot in this graph, would be an instance where we gave the robot precisely those commands, and then it ended up at a different location. So this reflects this idea that the mobile robot, even though you give it the same commands each time, right, there will be some stochasticity in how it executes those commands. That has to do perhaps with the floor, the type of the floor, whether the wheels are turning in a precise fashion, and so on. Okay, so I mean, it's a piece of engineering. It's a physical model that's not perfect, so that's why it will end up in different locations. And many decades ago, well, maybe not so many, but I guess a few decades ago, this was a big problem, because when researchers started working on mobile robotics, they designed some great robot that had some wheels, and then the idea was, let's get the robot to go from location A to location B, maybe go to the fridge, fetch a beer, and then come back, right? And then the problem is that, what you observe here is that the robot, each time you give it the same commands, it ends up in a slightly different location. And then, so if you use an odometer to just keep track of the commands, that doesn't tell you what is the location of the robot, right, the robot might end up in a different location, and so it was common for a robot to get lost within a few minutes. Okay, so that was very depressing because, I mean, those robots were, you know, great pieces of engineering. They had lots of capabilities and so on, but they would just get lost within a few minutes. So the solution to help the robot keep track of its location ended up being, again, to formulate this as a hidden Markov model. So here, if we formulate the problem as a hidden Markov model, we could say that the state corresponds to the coordinates of the robot on a map, and then the observations could be distances to surrounding obstacles that might be measured, let's say, by a laser rangefinder, a sonar, or even a video camera. Okay, so like a depth camera. So here, the idea is that, yeah, we have a state that's the coordinates. It's hidden. We're not sure what it is. We have observations that corresponds to measurements from some sensors. These are examples of sensors. And then the idea is that you see, if I'm standing in front of an obstacle, and let's say I'm the robot, and then I've got a laser rangefinder, then the laser would shoot a beam of light that would be reflected, and then either the time it takes or some other information would tell me roughly the distance to the obstacle, right? And then if I have an internal map, right, and then I would know that if I see an obstacle at a certain angle and distance from me, then I must be at possible locations on the map. And then the idea is that based on this, then you can infer location. Okay. Now the problem is that those measurements are noisy as well. Okay, so the classic problem is if you shoot a beam on a mirror or a piece of glass or some surface that does not have any texture, it might get reflected in a way where it will think that there's no obstacle because it doesn't get reflected back to the robot, but it gets reflected into a different direction. And then as a result, it thinks that there's no obstacle there, or the obstacle is much further. And then if you consider sonars, so sonars are in fact extremely noisy. So in general, you know, any sensor, there will be some type of noise, and you need to take that into account. So the idea is that then you can model this as a hidden Markov model, where you could say that whenever you give the robot a command, then the robot will go from a certain state, which is its location, to another state, which is the next location. And then this here has some uncertainty because, as we saw in this picture, you see I give precise commands that are always the same, but then the cloud of points illustrates the fact that on different instance, right, then the robot ends up at different locations. So it's stochastic. Right, so here I'm going to model this with a distribution. Then I do the same thing for the observations. So here the idea is that the robot is in some location. Let's say it sends a laser beam and then measures the distance based on that. Well, it's not going to be precise. And again, we should have a distribution for the type of observations or measurements that the laser range sensor will report. Okay, so with this information now, the problem of localization of the robot is the following, where you're essentially asking what's the probability that the robot is at a certain location given all the sensor readings that it has received so far. Right? So in general, it doesn't know, and it will never know for sure its precise location, but it has a stream of sensor measurements. These are observations. And then it should infer based on that what is the current location. Right? So the problem of localization can be formalized in this fashion, at least in this probabilistic setting. Okay, so more generally, we can say that with a hidden Markov model, there are several classic tasks. So what I've talked about so far is what is known as the monitoring task. So you have some observations up to time step t, and then you're trying to monitor or to estimate your current state at time step t. But then some other common task might be to also predict some future states. So let's say that we want to predict the stock market or predict the weather, right? So it's not just about estimating the current weather, but maybe predicting what the weather will be in the future. So I will have, let's say, some measurements about wind, temperature, and so on up until now. And then I'd like to predict perhaps the temperature tomorrow. So that's some state in the future. In some other situation, we also care about estimating some hidden state from the past, given that I've received observations up until time step t. Okay, so this is known as hindsight. And then another common task would be to generate the most likely explanation. So I've got a sequence of observations and I want to explain them in the sense that I want to try to estimate what would have been the corresponding sequence of states that produce those observations. So yeah, so these are the common tasks. And now an interesting question is, what algorithm should we use for that? So in the interest of time, I'm just going to talk about the first two, but then there are some related algorithms regarding the others. Okay? And in fact, this material is also covered in the AI class. At least those who took AI with me would have seen this. And then same thing for the machine learning class. This is also often covered in the machine learning class. So that's why I will only talk about those two for now. Okay, so for monitoring, again, the problem is that we want to compute the probability of ST given O1 through T. This is important for robot localization, as we saw. Another common one could be patient monitoring or any type of monitoring where we're trying to estimate the hidden state at a certain time step. So to do this, if we already have a model, let's say we already have a transition model and then an observation model, then we can compute this estimate of the current state based on some equations, and then we would arrive at a recursive equation here that shows that the estimate at time step t depends on the estimate at time step t minus 1 times the transition model, where we sum out the previous state, and times the observation, so that we can reweight based on the actual observation that we saw. Okay, so this derivation here shows how we can arrive at this equation. So we first start by applying Bayes' theorem. So it gives us this expression. Then we're going to simplify this by exploiting conditional independence. So essentially here, OT only depends on ST. It does not depend on the previous observations. We can simplify that. Then I'm going to introduce ST minus 1 by marginalization. So here if I introduce ST minus 1 in this term and then I sum it out, it's the same thing. And then finally, I will apply the chain rule to separate this term into two factors. So ST given ST minus 1 and then ST minus 1 given all the observations. And then finally, I can use conditional independence to simplify this one to just depend on ST minus 1, and then I get my final expression. Okay, so here this is a simple derivation that shows how we can estimate in a recursive fashion the probability of the current state given all the observations up until now. Okay, so we can summarize that into an algorithm that is known as the forward algorithm. And so here for this algorithm, we start with some belief about the first hidden state. And then so we would take into account the first observation. That would give us a posterior. And then after that, we apply our recursive update to get our belief at every time step given all the observations up until now. Okay? Any questions regarding this? Okay, good. So yeah, so this should be something that most people are familiar with. Now, we can generalize this to also do a prediction. So the difference is that now we're going to compute the probability of some state in the future as opposed to just the current state. So there's a similar recursive derivation. Okay, so we can compute this based on the previous state st plus k minus 1. So this is still some state into the future, right? So then we'll have a recursive update for that. And now we can combine this with what we saw for the forward algorithm into a more general forward algorithm, where what we do is we first compute our belief or the distribution over st up until the last time step where we've observed something. And then after that, we start making some predictions, again by computing forward. So now we're going to increase k, right? So, we're going to increase j up until we reach k. So this will essentially correspond to making predictions about future states up until we reach a time step that we care about. Okay, so again, two simple algorithms. Any questions? Okay, good. Okay, so let me quickly go through a case study. So this was some research that I did here with some students many years ago. So this was in the context of activity recognition, and then we used some hidden Markov model to infer the activities that were performed by a user. So here the idea is that let's say we've got some users of a walker. So a walker is a device that is used often by older people or otherwise injured people to help maintain balance. What we did is we instrumented the walker. We put a camera that's looking backward so we can see the legs of the person, and then another camera that's looking forward so you can see the environment ahead. Okay. Now, with this, what we were trying to do is to estimate the activities of the person given some sensor measurements. And then in particular, the measurements that we used were based on some accelerometers. So we had the forward, lateral, and vertical acceleration. We also had some load sensors. So all the legs here were modified to measure how much downward pressure the person is exerting on the walker. And then we had a wheel rotation counter. So all of that was being sampled at 50 Hertz. And then we wanted to infer what is the person doing with the walker based on that information. So here what I mean by activities, the choices for activities were essentially that at any point in time, maybe the person is simply not touching the walker. The person could be standing while holding the walker. The person could be walking forward, turning left, turning right, walking backwards, sitting on a walker. The person could be reaching to, let's say, pick up an object on the floor, going up or down a curve, and so on. Okay, so these are possible activities. And then the reason why we cared about trying to estimate those activities was because in the context of walkers, and especially for older people, one big risk are falls. Okay, so with older people, if they fall, then they might be at risk of breaking a leg, breaking a hip, having some severe injury, and then once you reach a certain age, this could be something that you might not recover from. So it could be quite problematic. And now the interesting question is, when is a person at risk of falling? Okay, so this was some research done here with colleagues in kinesiology, and then we wanted to understand, for instance, let's say you consider somebody who had a stroke before and then they're partly paralyzed on one side. Maybe when they do the turn on one side, they're not going to be as agile, and then they might be more at risk of falling, right? Or maybe it's the turn on the other side, or maybe it's when they try to sit on a walker, or, so we'd like to understand what are the triggers, or at least when is a person more at risk of falling. And therefore, if we can at least recognize what is the person doing at any point in time, then that's a first step. Okay? So this was the goal in this work. So we modeled this as a hidden Markov model. So the idea is that the different activities correspond to the hidden states, and then the sensor measurements correspond to the observations. And here what's a little special is that you see we had 8 sensor measurements at any point in time. So that corresponds to 8 observations per time step. But I mean, this is still a hidden Markov model, just maybe a little more fancy, but it's a hidden Markov model. And then this is the parameterization that we worked with. And then we estimated the parameters of this true maximum likelihood, both in a supervised and unsupervised fashion. And then we ended up with a working prototype that was able to recognize when people are walking. Okay, so I will play this video next class. Okay, so this is a video. I will play it next class. Let's stop here, and then yeah, we'll reconvene on Friday. In this demo, so this was one of the instances where we had a resident at Winston Park who went through the walking course that I just explained. And then you'll see in this field of view here the legs of the person. So this is the camera pointing backwards. And then at the bottom, you'll see the 8 sensors, and then their measurements will fluctuate as the video progresses. And finally, on the right panel here, we've got the 13 behaviors or activities, and then the correct behavior will be highlighted in red. This will be the behavior based on one of the researchers who went through the video sequence and essentially labeled manually what was the person doing at any point in time. Okay, so this was just for evaluation purposes. Obviously, in practice, what we want to do is not label these things manually, but then use our algorithm to automatically recognize what is the person doing. And then so the predicted behavior based on our algorithm will be in blue. And then whenever blue and red match, then it means that it's recognizing correctly. And when they don't match, then I guess there's a discrepancy here. Okay. Okay, so here we go. So the recording started. So this is a lady at Winston Park, and then she's going through the walking course. So she's, in fact, just getting into the starting position. And then you can already see at the bottom some of the sensor measurements that are fluctuating. And then you see here, for instance, she was walking forward, so both red and blue were matching. Now, once in a while, you see there's some discrepancy. So then it means that the algorithm is not perfect. Okay? But otherwise, it will be tracking fairly well the overall activities. Any questions regarding this? Yeah?
Was the course followed in the same manner every time, or were the tasks varied in terms of their sequences?
Yeah, good point. Okay, so yeah, so here the course was always done in the same way. And yeah, this has an impact on the model because it induces a bias in how the activities are performed. And it's not as general as it could be. But for the purpose of doing an experiment, in terms of the logistics, it was actually quite complex to just get this set up and do it. So that's why we still just went ahead with the same course and then just got everybody to go through that same course. Yeah.